Hey everybody, this is 11D, make the rope horizontal. The scenario is two people are standing on equal height buildings, are lifting a box of mass M between the buildings using two ropes. The people keep the two ropes at the same length between their hands and the box so that the rope makes an angle theta with the vertical there. So that's theta with the vertical. That's not how they always draw it. So very first thing they want us to do here, I'm going to switch back to this picture in just a second. It says on the dot below that represents the box, draw and label the forces exerted on the box at the moment in time when the box is at rest. Okay, so I think that we get here that we're going to have a force of tension from one person on the right here going this way, and a force of tension from one person on the left going this way, and the force of gravity coming down like that. So let's go ahead and draw the force of gravity here with my Blue Lagoon marker. So 1, 2, 3, 4, I'm going to draw it down and I'll label that the force of gravity. No reason to draw it 4, it's just a number that will work out well here. So now, before I actually draw all of this, they do not want you to draw components if this was a question on a free response of the actual AP test. But I'm going to draw components just for a reason to talk about how I know sort of to draw this. These two ropes together with their upward pull must balance this one downward pull of gravity. How do we know that? Because it's not accelerating in the y direction. So that means I have a total of 4 boxes down here. From the one rope on the right, I'm gonna draw 2 boxes up and I'll call this force of tension right y. And I'm gonna draw the same thing over here. I'm gonna call this force of tension left y. And so I know those two components have to be there to balance this out. Now, how far I make it to the side doesn't really matter. I arbitrarily drew it to the 2 to the right, and whatever it is, I would have to draw the same amount of boxes to the left, because we also know that it's not moving to the side. And so those forces sideways must also balance out. So you could call this force of tension right x, and this force of tension left x if you wanted to. But again, unless they told you to, you wouldn't even have to. There's nothing in this problem that tells you you have to draw those components here. What they would really like to see probably is this right here. So I could have just skipped this right away and drawn those two. And so we again would know that the upward pull from these two has to balance the combined upward pull has to balance the downward pull from force of gravity, and that their sideways parts would have to be equal to each other. So now, next part here is it says derive an expression for the magnitude of the force of tension in the two ropes in terms of mass, theta, and fundamental constants. All right, so if we look on here, this gets kind of confusing the way I've drawn these components right here. I actually could have also drawn them, the two y ones right here, like here, and then the two x ones right here and right here. I would get the same box, the same logic that I just applied. And the reason I want to do that for a second is they said that they measured this angle theta from the vertical. So when we talk about theta, we're talking about that value right there. So actually our vertical components are gonna be the adjacent side to the angle. And since we're using the adjacent side, we'll be using the cosine functions there. So going back to this, I know that balancing out my y forces, that my 2 force of tensions in the y together, because they're both going to be equal to each other, have to balance out the force of gravity. So how do I find that force of tension in the y direction? Well, it's going to be the overall force of tension multiplied by the cosine of the angle. Because again, since they're giving the angle relative to the vertical, the y is going to be the adjacent side. And that will equal capital M times G. So we've just about got it there. Now all we have to do is divide all our other values to the side. So it'll be capital MG over 2 cosine theta. don't know why I made my S so big there. And so that is the equation for our force of tension there. Last part for this one, they say the graphs above show the values of sine of theta and cosine of theta for angles between 0 and positive 90 degrees. The two people notice that as the box rises at a constant velocity, the force they must exert on the ropes becomes greater and greater, and they cannot make the ropes horizontal no matter how much force they exert. So use your equation from part B and one or both of the graphs above to explain why the people have these experiences. Okay, so one thing is our equation involves cosine, so let's focus on the cosine graph right here. And so look at this graph right here. As they said, they try and pull it more and more vertical or more and more horizontal. Well, remember, we're measuring from the vertical. So the angle is approaching 90 degrees. So the angle here is approaching 90 degrees. And if we look on this graph right here, as the angle approaches 90 degrees, cosine of the angle approaches, see, once we reach 90, 0. Well, let's look at our equation again here. Cosine of the angle is in the bottom of the fraction. So when the bottom of the fraction approaches 0, that means that the force of tension is going to approach infinity. So it would take infinite tension to make this thing perfectly horizontal. And the way to think about that is you're always going to have some amount of y force to cancel out the force of gravity there.